Hey everyone, it's CircusSec.
Today we've got an exciting adventure ahead as we tackle the AndroCat machine from Hackthebox University TFA. Get ready for some Android exploitation fun where we'll dive into cross-site scripting vulnerabilities in a web view, snatch up insecure shared preferences, and even explore the world of cross-site scripting in PDF generation. But that's not all DSU. For privilege escalation, we'll be turning the tables by taking advantage of a node. Data Service Manager web app running with root privileges. It's going to be a thrilling ride, so buckle up and let's get started. We've got a download and an IP on our hands. First things first, let's scope out open ports. I prefer using RustScan for this task, but use whatever tool you're comfortable with. Only found ports 22 and 80 open. Nothing too exciting. Let's check out port 80. And there we have it. The default Nginx page. We can fuzz the directory here and look for a virtual host, but since we have a downloadable at our hands, why not dig into that? We got our hands on an Android app to let the exploration and discovery begin. Opening it up in JADX, we're heading straight for the code goldmine, starting with the Android manifest. The Android manifest should reside within the resources directory. The Android manifest is a crucial file containing metadata for an Android application. Its significance cannot be overstated. The application requires a minimum SDK version of 29, which is Android 10, I think, while its target SDK version is set to 33, lining with Android 13. Apart from these specifications, there isn't much else that piques our interest. Let's check out strings.xml. Crucial XML file housing the strings utilized by the application. Taking a look, there seems to be a lot of unnecessary strings here, I think. There are two domains worth exploring. But first we have to add the domains here. Let's attempt to access these domains through our browser and see what we're dealing with. It seems we have two API endpoints utilized by the application. Let's go ahead and open the app to explore further. Analyzing the main activities login function, it appears it utilizes the volley library for making requests. Upon receiving a response, it checks if the token value is not empty. If not, it stores the token in shared preferences. Additionally, if there's an admin token, both tokens are saved in shared preferences, and the user is redirected to the admin activity. However, if there's no admin token in the response, the user is redirected to the home activity. Let's investigate the implementation of shared preferences where the application is storing the token. Well, it seems the application is not using encrypted shared preferences. Shared preferences, essentially an XML file, is stored in the application resource directory. This means that if someone can access this file, they can easily retrieve the token, highlighting a potential security vulnerability in the implementation. Anyway, let's move on to the home activity since we currently don't have any means to access it, so there's no need to spend more time on it. The home activity utilizes a web view, allowing the rendering of HTML, JavaScript, and CSS within the Android app without the need for a separate browser. Upon closer inspection, there appears to be an interesting piece of code. So the web view is configured to enable JavaScript DOM storage, and it intercepts resource requests. If any request's path starts with local _ cache, it retrieves the path of the cache directory, which is inside the resource directory. It then combines this path with the URL's path, checking if the file exists. If it does, the response is simply returned from that file. All right, let's proceed to explore the admin dashboard activity. The admin dashboard activity have a navigation bar, and depending on the selected option, it redirects the user to either the attendance, tracking activity, home activity, or main activity. Since we've already examined the home and main activities, let's shift our focus to the attendance tracking activity and see what secrets it holds. When a button is clicked, it triggers a request to the export attendance endpoint and proceeds to download the associated file. This code initiates a request to the attendance endpoint and then maps the received data into a table. Let's proceed and open the app to explore further. Now for the emulator, I'm using Android Studio, but feel free to use your weapon of choice. But before we dive in, our first step is to configure burp in the Android emulator to intercept requests. Let's set up our burp proxy to listen on all addresses. We already got the burp certificate downloaded. Let's proceed to transfer it to our emulator and install the Campus Connect application. The certificates have been copied to our emulator. Now, let's proceed with the installation. I'll opt for the straightforward approach by navigating to the settings, then to security, more security settings, encryption and credentials. Install a certificate. Finally, I really hate this much clicking, but it's easy. Certificate is installed. Now let's add proxy. Navigate to the networks, then internet, then edit the Wi-Fi settings. Click on the top right button to add a proxy. Everything is set up and ready to go. Let's launch the app. The login page greets us, and we even have the option to register. Let's move on and log in. After logging in, we get a forum interface. In the top right corner, there's a post button. Let's try sharing something. We came across an interesting note mentioning that all posts undergo review by a teacher. Let's check if the application is susceptible to XSS, starting off with a simple image tag to avoid any potential filters for sending our payload. Let's start a web server. This way, if our image tag renders and triggers a request, we'll know our payload is working. Our image tag successfully renders. Now, let's wait and monitor our web server to see if any additional requests come through. Fantastic. We've received a request indicating a successful HTML injection, which can be promoted to XS. Now, if we look at the implementation of the web view, so the web view is configured to enable JavaScript DOM storage, and it intercepts resource requests. If any request's path starts with local _ cache, it retrieves the path of the cache directory, which is inside the resource directory. It then combines this path with the URL's path, checking if the file exists. If it does, the response then simply return from that file. There's a big problem with this implementation. Let's look at the Android resource directory structure. Let's grab shell on emulator using ADB shell. Now to data directory. Navigating through it, we find a campus connect. The cache directory and the shared preference directory are there. And upon looking inside the shared preference, we find the user.xml, which stores our token. Let's say, for example, if we make a request to the specified URL with a path starting with local cache, the application intercepts this request. It then extracts the last segment of the URL. Since the application merely appends this segment to the cache directory path, we can perform a traversal by using .. / and potentially access any file in the resource directory, including the shared preference file that holds the auth tokens. Given that we've already identified an XS vulnerability, let's leverage it to steal the user. XMLs for a teacher potentially contain the admin token. Time to craft a payload and proceed with the extraction. We've got a function named getFile, classic start. Right? It takes in a path and a callback. This is where the party begins. Next, we whip up a fresh XML request. Here, we're configuring a get request to a random domain with local _ cache as the path. We then include .. / in the path, followed by joining the URL encoded path.
Moving on, we're setting up the onload event listener, which handles success. So when our request hits the jackpot, it fires a callback with the response text. On the flip side, the onError event listener catches any hiccups and sends a null to the callback. the send method fires off our request. Now, we're calling getFile with the file we want to steal and a callback. What's the callback doing? Well, it's redirecting the current page to our web server, and we're putting the file data as a query parameter in the URL, so we will get the file data in our web server request log. Now, we can craft our final payload. We'll utilize an image tag, setting its source intentionally to trigger an error. Then, we'll attach an on-error event listener that executes our JavaScript code. We're essentially creating a script tag, setting its source to our script, and appending it to the body. Let's copy this payload and send it using burp seat. Make sure to escape the double quotes to avoid breaking the JSON format. Now let's wait. There it is. Let's copy it to burp suit, decode the encoding, and dive into the details. Great, now that we have the admin token, let's use it to make a request to the export attendance endpoint that we discovered earlier. Let's replace this token with the admin token and change the header name and the host name. This endpoint returns a PDF, and it appears to be generated using headless Chrome. Let's check the content of this PDF. Let's configure our proxy to automatically include the admin token header in every request that passes through, eliminating the need to manually add it repeatedly. Upon receiving the PDF, we observe all users and their attendance, including our newly created user. Given that it uses headless Chrome for PDF generation, let's explore the possibility of an XS in the browser, starting with a basic image tag to test the waters. And indeed, the image tag renders successfully. Let's proceed and run a script tag to investigate the location of the page that headless Chrome is loading. Alright, it's loading result.html, and we notice it's using the file protocol. This implies we can load any file from the file system without encountering any complaints. Let's proceed and use an iframe to load a file. We've discovered a user named Rick. Now, let's explore if we can retrieve the SSH keys for that user using the same method. Fantastic, we've obtained the keys. Let's copy them and proceed to get a shell as the Rick user. Let's check if we have the permission to execute a command as the root user. Unfortunately, it seems we don't have the permission to execute commands as the root user. Are we part of any special groups? Just the KVM group, but it doesn't seem like we can leverage it in any meaningful way. Let's take a look at all the processes currently running as root. We've identified a node server running as root with peculiar parameters. Let's examine the current node version. It's relatively new. Now, let's delve into the significance of these parameters. Got it. So, this parameter essentially governs the system resources that the node application can access. In our scenario, the app seems to be utilizing process-based permissions. Let's explore this section further. This parameter restricts access to child processes and worker threads, and it also confines file read and write operations to specific, defined directories. Let's identify the port on which this app is listening and set up port forwarding to our machine, allowing us to access it through a browser. Well, these two are the API that we used earlier. This is it. Let's do port forwarding. We've landed on a service manager application with some listed services. However, given our current limitations on file read or write outside the app directory, it might not be fruitful to delve deeper. Let's shift our focus to the email settings instead. We have the option to edit an email template, and it appears to be using nunjucks. Clicking the preview button, it seems there's a possibility of template injection here. Let's grab a simple template injection payload and see if it works. Since template injection didn't work, let's attempt to read a file. So we can only read file in root service manager folder. No luck with file read due to the process-based permissions. Let's check if there are any publicly available CVE related to the experimental permission model. I'll search for CVA for the experimental permission. Great find! It seems we've hit upon a promising path traversal vulnerability in the buffer API, leading to a bypass in the permission model. Let's dig deeper into this by searching for information on this specific path traversal vulnerability using the buffer API. It seems like the link provides information on zip slip rather than the path traversal in the experimental permission model. Let's open this GitHub commit to get more clarity. Absolutely, the patch is crucial, but we're particularly interested in the test case that demonstrates how to exploit this issue. By analyzing the commit history or reverse engineering the changes made to patch the issue, we can craft an exploit even for bugs without a publicly available one. Let's attempt the path traversal with template injection. By utilizing the buffer API with the allowed folder being the root service manager, we can traverse back and potentially bypass the permission model, allowing us to read any file. Let's check if we can read file that we are allowed to read, just to check if our payload is working fine. Now let's try to read a file that we can't read, for example the SSH keys of the root user. And there you have it. If you found this video helpful, don't forget to subscribe and hit the like button. Feel free to leave a comment below letting us know what you'd like to see next. Until next time, see ya!